Part question 2. Okay, still in the 2018 part question 2. Elements sodium to argon form the third period of the periodic table. Explain the decrease in atom size going across the third period from sodium to argon. Okay, so you don't actually have data on argon because argon is a monatomic, so we don't have anything in terms of covalent radius. But we can get sodium. Sodium is 154 picometers, ChH. Okay, and we can get as far as chlorine. Chlorine is 99. So argon would be smaller still. So what we're looking for is that we have increasing nuclear charge or number of protons, meaning that they can hold the electrons in closer, which is why you get a different atomic size. What you've not got is no increased shielding. You get no increase in shielding because you're not increasing the number of shells. That's it. Okay, elements in the third period form chlorides. Structures of 3 are shown. Circle the structure of the molecule above that contains bonds with the lowest polarity. Okay, so you're just looking for electronegativities here. Right, they're all going to chlorine, which is 3. So you're not going to have to do anything to that. We're just looking for what is the least difference between. Okay, so going and looking this up, silicon is 1.9, phosphorus is 2.2, and we're going sulfur is 2.5. Okay, so lowest polarity, smallest difference between 3 to this is 3 to 2.5, so I'm circling that one. Explain fully why of these 3 chlorides, silicon tetrachloride is the most soluble in hexane. Okay, so here's your silicon tetrachloride. Explain fully why it is most soluble. So what you need to say for a start is that hexane is non-polar. Okay, if you have something which is non-polar, then the thing that's going to be most soluble in it is something which is non-polar. If we look at the silicon chloride, although we have quite a strongly polar bond, what you have is a non-polar molecule. Okay, so we need to link your polar bonds are basically cancelled by symmetry. That's not how you spell that. There's extra letters in there. Cancelled by symmetry of the molecule. So it's non-polar. And like dissolves in like. That's it. Okay. C. Silicon tetrachloride can be used to make silicon nitride, compound found in cutting tools. Silicon nitride has a melting point of 1900 degrees C, does not conduct electricity when molten. Explain fully in terms of structure and bonding why silicon nitride has a high melting point. Okay, right. Basically, high melting points are either going to be covalent network or we're looking at kind of large lattices, so ionics, metallics. Melting point this high with things which are non-metals means we are looking at a covalent network structure. And that means that in terms of the structure, this network means that they are all interlinked. Okay, and if they're all linked with strong covalent bonds, then to melt it, you need to break all those. So we have interconnected all together. Every single connection is a covalent bond. If I want to melt it, I need to use enough energy to break covalent bonds, and they are strong. There we go. Part 2, an equation for the formation of silicon nitride shown. Calculate the atom economy for the formation of the silicon nitride. Okay, so silicon nitride is here. Atom economy. Atom economy straight out of the data book. Atom economy is going to be your mass of desired products over your mass of reactants. Okay, so our mass of desired products is just, we're only getting 1 mole of this, so 140.3. Mass of reactants, being careful. We have got a 3 and a 16 in here, and you've got to take them into account. So that's going to be 3 times 170.1 plus 16 times 17. Okay, so that is 140.3 divided by 782.3. Times it by 100 to get into a percentage gives you 17.9%, or in the mark scheme they were also quite happy with 18%. That's it. Okay, we've got our diagram question. We always got one. Okay, aluminium, another element in the third period, also forms a chloride. Aluminium chloride is prepared by reacting aluminium metal and chlorine gas. Okay, so we're looking for the reaction between them. It says it's passed over heated aluminium foil, forming aluminium chloride. Hot aluminium chlorine gas and unreacted chlorine gas are passed into a flask where the aluminium chloride cools to a fine white powder. For safety, it's important that any unreacted chlorine gas can escape from the flask. Complete a label diagram to show an apparatus suitable for carrying out this preparation. Okay, so I would put this one just into a flat, right? Okay, maybe I'm going to have to draw this maybe to the side. Okay, so I need to put this through something which allows me to put a heated aluminium foil. So I'm going to put this as my aluminium foil, and I'm going to put a heat source here, probably a Bunsen, okay, and that will allow it to pass through over the top of the aluminium foil. Okay, then for my collection, it says that it goes into a flask, so let's just make a flask. Okay, and we would have our tube coming in and going down. Oh, terrible diagrams I draw, but I draw them very neatly when I've got a ruler and it's on paper, just not on this. Okay, and then it says that it forms a white powder at the base. Okay, and that's your actual aluminium chloride. It says that you have to have, the gases need to be able to escape, so you can either leave it like that, or you can choose to put just a kind of little tube that allows it to escape, so that we have not an issue. And that's pretty much it. If you wish to speed up the condensation of it, which you might want to do, and I'd drawn it originally before, it didn't really say anything on the mark scheme on this, but I might have put the whole flask into an ice bath, just to speed up your condensation. Okay. Explain why the aluminium foil needs to be heated at the start of the preparation despite the reaction being highly exothermic. So basically, once the reaction's going, it starts releasing quite a lot of heat, but to start with it doesn't. So what you have to do is originally supply the activation energy. That's all we're saying. So it's the initial activation energy. At that point, once it's exothermic and it's generating heat, then that will also provide activation energy for continuing the reaction. And that's it.